So the first part is the market assessment outline. I'm going to briefly cover wider market assessment, go through a case study of Ethiopia, and come out with some next steps for Ethiopia and wind empowerment. So as I said, the technical aspects of wind turbines are quite well known, but the social and economic are not so well known. Small wind is a very niche market. It's not applicable everywhere. This world map shows where there is wind and where there's not. And in some areas, such as the Congo, there's just no wind, and it's very unlikely that a wind project will be successful there. Whereas Patagonia, there's obviously a lot of wind, and it's likely to be successful. In the middle, maybe some more assessment is needed for the wind resource, and also other technical and social aspects to it. So, targeted investment. If an NGO wants to spend some money on rural electrification, it could spend a lot on wind, and then it will end up a few years down the line that wind doesn't work, and then waste that money, which could have been spent in a better area. So if a company or an NGO is thinking about investing in wind, the where comes from the market assessment delivery group, and the how to implement it comes from the delivery model. So the methodology for doing a market assessment is one we're going to develop, and the 4 examples that we've got today will show you different ways of doing it. And the first is in Ethiopia. So in Ethiopia, about 84% of the people don't have access to electricity. That's unlikely to change. The grid is too expensive to expand the grid for many areas. And for rural electrification, solar is being used. But to purchase solar, you have to purchase it from China or from Europe, which means that money from the country goes abroad, and they lose the value chain, so it's called. There's a lot of interest in local manufacturers to boost local jobs. As a background, myself and John went out to Ethiopia in December last year. We attended a UN conference where we ran a pilot course building a 1.8 metre wind turbine. And during that, we found out the costs for materials and had interviews with practitioners to conduct a market assessment, which was done as part of my master's dissertation. So the existing literature about Ethiopia, there's a lot of maps of Africa and the world, what is the most suitable technology for rural electrification. And this covers solar, diesel and microhydro. But there's nothing at the moment done on small wind, or very little. So these maps take into consideration solar resource, wind resource, subsidies for diesel, and map which areas are better for which technology. And you can see for Ethiopia, the red lines are the grid, the yellow is off-grid PV, and the purple is mini hydro. But we're interested in
the potential, or I mean, I assume not everybody living in the yellow have off-grid PV.
No, but it's the most economical option for them. If an NGO is working in that area, it's the most economical. And the idea is to try and include small wind into these maps. So the methodology involves a lot of data collection. You start with a system design, looking at load profiles of what you're going to be providing in terms of electricity, a technology overview of the types of wind turbines you're using, and any other equipment such as solar panels or diesel generators. We'll have a look at the energy resources for solar, wind and diesel, and mostly, because it's a market assessment, look at the costs, but not just the component costs of wind turbines, but the surrounding costs of running a business, installation and manufacturing costs, and operation and maintenance, which we know yesterday are a big part of the costs. The data sources come from primary field work on the markets, finding out how much things cost, local suppliers, chatting to renewable energy practitioners, also available literature from journal papers, wind empowerment groups, and online resources such as Arena and SINA, which we'll see later. And for this study, the data analysis was done in a program called HOMA, and some GIS mapping was done, which we'll show you. Here's the energy resources in Ethiopia. The wind is very variable, high in the east, low in the west. The solar is also very variable, very high in the north, less so in the west. And the cost of diesel has been increasing over the last 10 years, and this has been modelled for the predicted increase by 2018. Put some websites here There's a lot of really useful wind data and solar data online. Aran and the Geo Catalog. And if you have GIS software, you can import it directly and then do cross-analysis of resources. It's also important to look at how complementary the wind and the solar resources are. If it's windy at the same time as it's sunny, then wind turbines probably won't be that much use because you might as well use solar power. But if, like in Scotland or in Ethiopia here, if there's a season where there's low sun but there's high wind, that's where wind turbines are optimal. And you can see here in the west of Ethiopia, wind and solar are very complementary. Sorry, in the east, they're very complementary, and in the west, they're less complementary. And this data you can feed into Homer to analyse how well it works. It's important to think about what the off-grid system is going to be supplying, and you need accurate load profiles for what the energy is going to be used for. In Ethiopia, the most accurate load profile I could find was we looked for productive uses of energy. And this is different between education and communication, which is lights and phone charging. Productive use of energy is something where you can use the energy to earn money. And in Ethiopia, a standard business model is a barbershop. Everyone needs a haircut, and everyone will pay for a haircut. So there's quite a few entrepreneurial renewable energy teams that are doing solar barbershops. And this is a commercial centre which has got a beauty shop, a razor, a fridge, a fan, and exterior lights. Changing the world one haircut at a time. And Homer models the load profiles with some randomised factors so that people aren't switching the loads on at the same time each day. So that's a load profile that you get out at the end. The choice of technology, which you're going to include in the system, for this we did a hybrid system with wind, solar, diesel, batteries and inverters. And in Homer you need to know the capital cost, the replacement cost, the operation and maintenance and the lifetime for each of those components. And you want those to be as accurate as possible. The lifetime or the operation and maintenance costs can really change the economics of the project over 20 years. So this needs to be gathered ideally first-hand in country from local suppliers. This is the cost of the wind turbine itself. It's split into turbine materials, tower, electrical system, which doesn't include batteries and inverter because they're treated separately in Homer, business costs, and manufacturing and installation costs. So you're really looking at the whole business that's building these wind turbines and installing them. The reason there's two sets, well there's three separate, the 6 columns, is I've modeled 3 different distance to site from where the turbine is being built to where it's being installed, because there's going to be an increase in transport costs. There's also low and high sensitivities, and a sensitivity value is if you're not too sure, you have to guess. And the sensitivities for this is an increase in component costs and a reduction in magnet tax. The operation and maintenance increases quite a lot if there's a big distance to site. And this is, if it's more than a day and a half of site, the operation and maintenance costs increases quite a lot. Homer is an optimization tool. Some of you have used it. I know Roland has. On Wednesday we'll go through it if anyone's interested in the poster session. These are the results. You have global solar along the top and wind speed along the bottom. And for different resources it tells you which systems are optimal. PV, if it's low wind, wind and Jenny in the green, wind and PV in the green, and wind only in the blue. And it tells you that for Ethiopia, if the wind speed is higher than 5.5, wind turbines are always more optimal. However, if the operation and maintenance costs are too high, then there's no option where the wind turbines are most optimal. So the operation and maintenance costs really affect the model. These were fed into GIS mapping, so for each area in the country, for that wind resource and that solar resource, this is what the most optimal systems are. In the south and in the east, wind turbines are suitable. Most of the country for the red PV is suitable. The transport network is important because that affects the operation and maintenance costs. The population and electricity grid is also important because you need to see where people are living. And the most important for Ethiopia was that the corresponding area of high wind, no grid, corresponds to areas of high civil unrest and terrorism. So there's maybe a link between the grid, lack of access to the grid, poverty, and civil unrest there, but maybe wind turbines could change that. So we're going to be doing a project in Ethiopia. We're continuing the market assessment. We're continuing the market assessment. We're continuing the market assessment. We're going to do some practical projects out there, and we'll talk about what the wind and power working group can do because it relates to measurement, technology, delivery models, and education. Sorry for overrunning. Thanks.